All right, so we're going to switch gears a little bit. We've been talking about calorimetry, but we will be talking about electromagnetic radiation. So we're going to move into Chapter 6. So our lesson objectives, we'll explain the behavior of waves, both standing and traveling. We'll describe the wave nature of light, and we'll calculate frequency, wavelength, and energy using the appropriate equations. First things first, a wave is a periodic movement that can transport energy from one point in space to another. We've seen waves all the time. When you put your finger in calm water, you make waves. Boats leave a trail of waves. We know the sound of waves. We can hear thunder, for example. In all of these cases, energy is being moved from one place to another. Sound waves are carried by air particles. Particles get bunched up in certain areas and sparse in others in a periodic way, just like this illustration. These particles hit our ears, and that is how we're hearing sound. Water does the same thing when you talk about waves hitting the shore, and waves can also travel via light. So that would be the wave nature of light. Your personal experience with waves likely includes seeing things like the picture on the right. When two wavefronts interact, they make what's called an interference pattern. Sometimes the waves add to each other and make the region of high amplitude, and sometimes they subtract and make a region of no amplitude. So that's illustrated on the left. If your waves line up, they add, and if they don't line up, you subtract. Now, when you're adding them, you would possibly call it magnifying, and when you subtract them, you would call it canceling. The two waves interacting here on the right make a pattern that has box-like shapes. You can see like little boxes there, like in through this region, and that's pretty common when you see wave fronts interact. You can see like a hash mark, or you can sometimes see shell-type shape. It depends on how they're interacting. You may also see them represented as audio waveforms. So those are the barcode-like things that have differing amplitudes for the lines. Those are 2D representation of interference patterns. So what are the parts of a wave? Waves have a wavelength given by the lowercase Greek lambda, a frequency given by lowercase Greek nu, and an amplitude given by capital A. Wavelength is the distance from one peak maxima to the next. You can also measure from trough to trough. Essentially, it is the length of the period of the periodic movement. Frequency is how many times a peak passes a point per second. This is count per second, given by hertz, Hz, or second to the -1. Those representations are interchangeable, and they're for the same idea, frequency. So if you ever see hertz, it means per second. Amplitude is how high the wave is from the top to the midpoint. When you increase the amplitude of a sound wave, the sound gets louder. When the wave is made of light, it travels at a maximum speed of light, 2.998 times 10 to the 8th meters per second, and that is given by the c, a lowercase c. Now, there is a relationship between wavelength, frequency, and speed of light. Speed of light is equal to wavelength times frequency. Observations tell us that nothing can go faster than the speed of light. Now, if we look at that equation, what happens to wavelength as frequency increases? So if you increase your frequency, that's the funky new weird V looking thing, what happens to wavelength, the funky 10? Well, wavelength decreases because they're inversely proportional. Speed of light is constant, and so if one goes up, the other one goes down. As an aside, the speed of light is dependent on the medium the light is moving through. So the speed of light in a vacuum is what we're representing here with the 2.998 times 10 to the 8th meters per second. But light is slower when moving through materials. At this point, let's talk about electromagnetic spectra. So you've probably seen this before, but here we go. When you put the wavelengths and frequencies on an interconnected number line, so you've got frequency on the top, wavelength on the bottom, obviously one side is going down and one side is going up. It's a little bit disconcerting, but they're inversely proportional, so it makes sense. You can label it with the type of light that occurs in each region. We're most familiar with the visible spectrum, but there are wavelengths that we cannot see with our eyes. Actually, most of them we can't see with our eyes. Many insects see with infrared light instead of visible light. Infrared is most closely associated with heat energy, so insects can see hot things. That's why it doesn't matter if there's sunlight out, the fly can still find you because you're giving off heat, and that is the light a fly sees. So you are like a big shining beacon to a fly that wants to suck your blood. Each region of the spectrum can be used to transmit different types of information and observe different things about matter based on how energy of the waves move from place to place. Okay, now here's an important relationship. Energy of a wave is equal to h, which is called Planck's constant. It's 6.626 times 10 to the negative 34th joules seconds. We'll talk more about that later. And frequency. Energy and frequency are directly related. So when frequency goes up, energy goes up. The book has an illustration of this where each part of the spectrum has a picture of what it can be used for. I'm going to stick to this illustration because it's less busy, but generally speaking, gamma rays have the highest frequency and therefore the highest energy. Radio waves have the smallest frequency and therefore the lowest energy. But when we look through this, we know that the uses for some of the regions because of the name of the thing. So when you hear X-ray, you think of images that you take of the bones of your body, right? You can see through your skin using an X-ray. When you see a microwave, you think of the appliance. You know that you can heat things up that way. Radio waves make us think of our radios. And it turns out there is still more to know about waves than just these things. Waves can be fixed to a certain location, or they can travel. Those that are fixed to a certain location are called standing waves, and those that can travel are called traveling waves. You are familiar with both. Tidal waves are traveling waves. Any string instrument works with standing waves. So standing waves have fixed ends, and therefore only certain wavelengths can work. This leads to quantized energy. Quantum meaning a very specific amount. This is what happens in bonds. The endpoints are fixed at the nuclei, and so that's why you get certain excitations at certain wavelengths. The nuclei fix the length the wave can travel. So on the left here we have a nice illustration of what happens when you try to fit a standing wave into a fixed location. So our two endpoints are more or less where the wave starts and stops. And you can have a half of a wavelength because we don't see the other side where you go down on this. You can have a whole wavelength where you go down and then up, or up and down, whatever you want to represent. And you can have 3/2 wavelengths, and you can keep going like this. These are all the places that you can have a standing wave. Anything short of that and you just don't get a wave like that at all. So as you increase the number of waves, you introduce what's called a node. That's this point where you go through the center where the amplitude is 0. So in this particular wave, we don't count the endpoints as nodes. How many nodes are there on the wave labeled 2? Super easy, right? There's just one. Now I want you to think about it. How many nodes would you have if we had 5/2 of a wave? Draw this out if you need to. There are 4 nodes on a 5/2 wave. So what about these traveling waves? Well, they can take on any wavelength, which is going to become important later, but we're not going to get to all of the things in just this thing. Okay, so let's try some calculations. Case 1. What is the wavelength in nanometers of a photon with a frequency of 6.5 times 10 to the 14th hertz? Now we have to remember that a hertz is also seconds to the negative 1. So we're first going to just take our general equation, C equals lambda nu, and we are going to solve for our wavelength, because that's what we're looking for. So we divide both sides by nu. Those cancel out, and we end up with just C over nu equals lambda, lambda being wavelength. Next, we plug our values in and we solve. So we have the speed of light, which I'm representing as 3 times 10 to the 8th meters per second. We have the frequency that we're given, and that's in per seconds, right? It's hertz. And when we look at this, we can cancel out the per seconds. Bye-bye. And so we end up with meters. But the question specifically asks for nanometers, so we have to do a little unit conversion here at the very end. And we use our 10 to the 9th nanometers in 1 meter, and we find a wavelength of 460 nanometers for this particular frequency of light. So case 2, what is the frequency in hertz of a photon with a wavelength of 250 nanometers? So the first thing we're going to have to do is figure out what's going on in our equation. In this case, we're trying to isolate nu, and so we divide both sides by lambda, which makes lambda cancel out, and we end up with c over lambda is equal to nu. Then we're going to plug things in, but we can't plug them in right away because c is in meters per second, but our distance is in nanometers. So we convert from nanometers to meters, and then we plug it in. Okay, in this case, we cancel out meters, and we end up with per second, which is a hertz. Yeah. So things to notice about this. You always are going to have to do some kind of unit conversion because we like to talk about wavelengths of light in nanometers, but our c equals lambda nu is in SI units, which is meters per second. So you just anticipate the conversion and you'll be fine. All right, what if instead we want to do an energy and wavelength or energy and frequency calculation? From the previous slide, we know that E equals h nu, and we know that c over lambda equals nu. So we can do a substitution. We can plug in c over lambda for nu, and we get E equals hc over lambda. So we've got two different cases here. We want to determine the energy of a photon of light with a frequency of 7.95 times 10 to the 19th hertz, which again is per second. So we take that and we plug it into E equals h nu, and it's fairly straightforward. Joules times seconds, the seconds cancel out here with the per second in hertz, and we end up with our answer in joules. Straightforward, didn't have to do any unit conversions, very exciting. In case 2, we have to determine the energy of a photon with a wavelength of 25 millimeters, which is a microwave. So we're first going to have to convert from millimeters to meters. Not that hard. We divide by 1,000. Now that we're in meters, we're going to use the E equals hc over lambda. H is a constant, c is a constant, we just plug everything in, and when we cancel out the units, they cancel. So we're going to cancel the per second with the seconds here, and we're going to cancel meters here with meters there. We end up with 8 times 10 to the negative 24th joules. Now I will warn you, when you go to put this stuff in your calculator, if you don't remember to do times 10 to the negative 34th as a unit, like if you're dividing by Planck's constant or something like that, it is very easy to do times 6.626, or rather divided by 6.626 and then do times 10 to the negative 34th. But if you don't put parentheses around it, what you're actually doing is divided by 6.626 times 10 to the negative 34th, and you will get ridiculous answers. So just be very careful of your order of operations when you're doing these particular calculations, or you will definitely get the wrong answer. All right, so let's try some more calculations of this type. Determine the frequency of light with an energy of 5.827 times 10 to the negative 15th joules. Okay, so we have an energy, we're looking for a frequency, we can use E equals h nu. So we solve it for nu, so we get E over h equals nu, and then we're going to plug our numbers in. And we find that joules cancels out by joules, and we get per second, or the hertz. It is both. Right, and you'll notice I carried my sig figs, but then I crossed one off, and that was an accidental rounding error. Even I do it sometimes. Case 4. Determine the wavelength of light with an energy of 1.837 times 10 to the negative 10th. So in this case, we're going to use the E equals hc over lambda, and we're going to solve it for lambda. So if we rearrange that equation, we get lambda equals hc over energy. Then we plug and chug. Okay. And we get a number that is 1.08 times 10 to the negative 15th, which is tiny. That is why we put things in nanometers, because it's less obnoxious to look at. To summarize, a wave is a periodic movement that can transport energy from one point in space to another. Waves have frequency, which is given by the Greek lowercase nu, wavelength, which is given by lowercase Greek lambda, and amplitude, capital A. Constructive interference makes waves have higher amplitude, and destructive interference makes them have lower amplitude. Standing waves have fixed ends, which leads to quantized energies, whereas traveling waves do exactly that. They travel. They can have any energy. And E equals h nu, energy equals Planck's constant times frequency. C equals lambda nu, speed of light equals wavelength times frequency. Whenever you're doing these problems, watch your units. You will end up with very crazy things if you don't. And h, Planck's constant, is 6.626 times 10 to the negative 34th joules times seconds.